Hello, everyone, and welcome back to Teach Astronomy. My name's Victoria, but you can call me Vicky, and I'm filling in for Matthew today, who normally helps out with Professor Impey's streams. But today we have Professor Impey here ready to answer some questions all about astronomy, astrobiology, astrophysics, and all that good stuff.
Okay, welcome everyone. These are the live Q&A sessions for the online courses that we have, our MOOCs, or anyone else who happens upon them. And I'm happy to answer any questions you have on astronomy. We'll be getting messages, or questions rather, both from email and the chat, but we actually have to get the email questions in a slightly indirect way, so it may take a little while. But anyway, floor is open for your questions.
All right, let's start with this one from Sahitya24. They ask, on Earth, time is calculated according to position of the sun. How is time calculated in space?
That's a good question. But also astronomy has always had two different ways of timekeeping, and it gives a hint of how we would keep time beyond the Earth. So on the Earth, there's always been solar and sidereal time. And, you know, this is true of astronomy, of course. We keep time by the stars, not particularly by the sun. And that's because the sun, the Earth's orbit of the sun is uneven. We have a varying speed to the elliptical orbit, and a varying rate of progress around the orbit. So if you kept time by the sun, there is a mean solar day, but there are significant variations about that solar day. So that's a limitation of keeping time by the sun. So a more sensible way to do it is to keep time by the stars. Obviously, as the Earth spins, the entire night sky goes through a cycle, and you can measure the time it takes for a star to rise or set. And the sidereal day is 4 minutes shorter than the solar day. So there's a small difference there, and that represents the fact that over 365 days times 4 minutes, you get 24 hours. That's the migration of the whole sky in one cycle of the Earth around the sun. So astronomers use sidereal time, timekeeping by the stars, and since the stars are at very large distances, tens, hundreds to thousands of light years, this is essentially how you would keep time in space as well.
All right. Next question is from David Learning. How do the properties of the Big Bang singularity compare to the properties of the Milky Way supermassive black hole singularity?
Well, it's an interesting comparison. So people wonder whether the Big Bang has in any way the properties of a black hole. It's a very different extreme event. A black hole singularity is the hypothesized cusp of density at the center of a black hole inside the event horizon. I say hypothesized because it's a non-physical property. To have an infinite cusp of density is not physical, not physically sensible. So it's indicating our theory of black holes is incomplete. If you project the universe's evolution back in time, there's convergence to imply an origin at also infinite mass density, which is like a singularity too, now for the whole universe. But that also is indicating that our theories are incomplete, because that's a non-physical situation as well. And so essentially physical theory cannot describe the very origin of the Big Bang as a singularity. So they're slightly analogous, but there's a very loose analogy, so I wouldn't follow it too far. And in each case, they indicate a limitation of physical theory.
All right. Next question we have from Prab1307. They said, good morning. If the Earth stops spinning around its axis, keeping other motions as it is, what will be the effect on Earth's gravity? And what are any other effects?
Well, okay, hypothetically, if the Earth stopped spinning and other motions stayed the same, so the orbit of the sun stayed the same, there would be an imperceptible effect on gravity, because obviously there's a centrifugal force associated with the spinning of the Earth, and that centrifugal force depends on your latitude. That centrifugal force is 0 when you're at the pole, because the pole is not really spinning, and then at the equator it's at the maximum. Now this effect is significant, it's real, and that's why space missions are launched at low latitudes. NASA launches its space missions at Cape Kennedy or Cape Canaveral, which is at the bottom end of Florida, which is the lowest point in the continental US. And that's because it's the lowest latitude and has the biggest component of centrifugal force. So that offsets the energy you would need to escape the Earth's gravity by some small amount. But it's a significant amount, and it helps in terms of rocket fuel. James Webb Space Telescope was recently launched by the Ariane rocket, which is from the European Space Agency, and they launch out of French Guiana, which is a former colony of the French, and it's very close to the equator, so you get a maximal assist from the centrifugal force. So the space programs around the world use this effect, but it's an imperceptible effect. You would not, if the Earth stopped spinning, you would not notice any difference to your weight.
All right. And we've gotten a few questions about this, and it's the big topic in astronomy lately. So did you want to talk a little bit about the James Webb Space Telescope that launched on Christmas morning? Maybe just a little overview about it.
Sure. The big picture overview is that the James Webb Space Telescope, long anticipated, a decade behind schedule, ballooning budget to close to $11 billion at the time of launch, so most expensive scientific mission ever in this country. I think something like Large Hadron Collider perhaps costs more, so it's not the most expensive scientific project ever, but it's pretty close. It's been a success so far, so it's a very challenging mission, long in the making. And the launch also much delayed. Even in the last few years, it kept getting pushed back a year at a time, a month at a time, and then eventually a few days at a time until it ended up on Christmas morning. The launch was successful with an Ariane 5 rocket built by the Europeans. The telescope is, of course, too large to send up fully deployed, and so it folds origami style into the casing of the spacecraft. And the biggest challenge is unfolding in orbit, or rather when it leaves the Earth's orbit to go to its L2 destination 1 million miles from the Earth. And in the subsequent few weeks, we've witnessed it go through the first parts of its unfolding, which you can do in space while it's traveling through a vacuum. You don't have to wait till you get to the destination to do this work. So it's going to have a while of traveling. And I think the most recent success, even as recently as yesterday, is the unfurling of the solar shield, which protects the telescope and keeps it at a very low temperature needed to do infrared astronomy. So far, it's passed these hurdles, these very difficult technical hurdles of unfolding the telescope and its various components while traveling through space. But there's a long time remains before this engineering work is complete, and we'll really know if the telescope is fully intact and operating at estimated sensitivity. So we'll have to take test data before we know that. That's a few weeks away.
Very exciting. All right. So we have a couple questions from email that I was able to grab. The first one is from Wendy Traver. Wendy asks, if all energy and matter were created in the Big Bang, where do astronomers hypothesize the surplus energy came from to produce the inflation that exponentially expanded the universe? And as a corollary, what is believed to account for dark energy's varying strength over time?
So the force for the expansion of the universe and then the creation of all mass and energy within it is presumed to have come, and this is true for inflation as well, is to come from the vacuum. It's a vacuum energy concept. And so inflationary theory has a scalar field, which is a physics term for a kind of field that can exist in the pure vacuum. And the possible vacuum states can allow for energy to be borrowed, if you like, violating conservation of energy for a short period of time, but sufficient to inflate the universe exponentially for that short period of time. So it's a question of vacuum energy, borrowing energy from the vacuum to inflate the universe, and then a more modest amount of energy required for the subsequent Hubble expansion. The question of whether dark energy is implied and whether that dark energy is varying with time is not clear yet. So far, astronomical observations imply that dark energy does not vary in strength, in direction in the universe, or over time. So at the moment, there's no sign that dark energy decays or has grown over cosmic time.
All right. Going back to some of the questions from our live viewers, Also, a lot of questions from new people from first-time chatters. Welcome, everyone. Thanks for finding our channel. We got one from Texadactyl. What have we learned about the beginning of this universe prior to about 300,000 years, like the first 300,000 years? This is beyond what info the CMB can provide.
Right. So the precision cosmology from the cosmic microwave background, the CMB, has been the great success of the last few decades in cosmology. We've learned an awful lot about the universe in detail from the microwave background. And that radiation dates from roughly 380,000 years after the Big Bang. Before that, our measurements are somewhat indirect. I'd say the strongest evidence we have of physical conditions early in the universe comes from the abundance of the light elements. So we see amounts of helium, of lithium, and beryllium. Beryllium is a tiny trace element, actually. So it's really helium-3, helium-4, and lithium, and deuterium, those 4 light elements, which were not produced in stars. The bulk of those light elements were made in the Big Bang when the universe was very hot. So we trace back time to when the universe was as hot as the center of a star, 10 million degrees or so, and that's the first few minutes after the Big Bang. And though abundance of those light elements measured out in the universe agrees very well with the Big Bang model, hot Big Bang model. So that's a very profound success of the Big Bang, taking it back to a few minutes after the Big Bang. That's very obviously incredibly early compared to 380,000 years. Beyond that, it gets much more speculative. The next landmark in the history, going backwards in time, would be about a microsecond, and that's when we think the matter asymmetry arose in the universe, where there are not equal numbers of particles and antiparticles, but a number of particles, almost no antimatter, and a large amount of radiation. And that event is traceable back to about a microsecond after the Big Bang. But we don't have a fully fledged physical theory for the cause of that asymmetry. So that's essentially where we run out of steam as far as talking completely knowledgeably about the Big Bang at very early times.
All right. Another question from one of our first-time chatters, H. Binham. Will Gaia and JWST data answer the Hubble constant question, and what do you think that answer will be?
Well, the Hubble constant question that's being alluded to is the fact that we have an issue at the moment in cosmology with the measurement of the expansion rate locally in the nearby universe, and that is called the Hubble constant. The Hubble constant is actually a parameter. More generally, it's called the Hubble parameter because it's varied with time, because the expansion rate has changed as the universe has accelerated and before that decelerated. So the local measurement of the Hubble constant disagrees by a small but significant amount with the inference of the expansion rate measured from microwave background observations, so the much earlier universe. And that dissonance or disconnect or conflict, if you like, whatever word you want to use, is a source of some anxiety in cosmology because it's not really going away. As far as resolving it goes, the James Webb Space Telescope is not really going to be a big player in the resolution of the Hubble constant. That's not what it was built for. It was built for kind of different purposes. It can't do the kind of survey observations required to make impact on that subject. Gaia, however, can. Gaia is a European satellite that's measuring the positions of a large number of stars, 1% of the stars in the Milky Way, about 1 billion. And it can use that to measure parallaxes and direct distances. And so it will nail down the local Hubble parameter, the Hubble constant, much better than we can currently. The precision of the Hubble parameter measured in the local universe is about 6%, roughly. Reducing that to 1 or 2%, which is plausible, will really indicate whether there's a deep problem in cosmology or whether it's just measurement errors and systematic errors that we didn't recognize.
Okay, for this next question, I'm going to roll a couple together because we have some people asking about the expansion of the universe. So as far as the expansion of the universe goes, what do we think is beyond the observable universe? Where is the universe expanding to? And will the universe continue to expand forever, or will it eventually collapse upon itself?
So try and answer all those in one go. The nature of the expansion is that it's a homogeneous expansion, which means every galaxy is moving away from every other galaxy. There's no privileged position in this expansion. However, we're located in a particular place, and the light and the information of the universe has to travel to us at the speed of light. So the limit of our vision is how far light can have traveled in the time since the Big Bang, 13.8 billion years. And that means there are definitely in the Big Bang model galaxies that have been moving away from us and are just at large enough distances that light can't have reached us in the time since the Big Bang. So they are a part of the expanding universe and we just can't see them. And that's not a bug with the theory, it's not a glitch, it's not a problem, it's just an inevitability of the finite speed of light. So there are definitely galaxies in the expanding universe moving away from us whose light we've never seen. And if the accelerating expansion is true from dark energy, we will never see them because as time passes in the future, they'll be moving even faster away from us. So if we can't see them now, we never will be able to see them. So that's part of the question. And the other part of the answer, of course, is that there is physical universe beyond the parts that we can see. That's just a limit of information, not a limit of the edge of space or time. As for the fate of the universe, as I've alluded to, if dark energy has the value that we measure with supernovae, that was a Nobel Prize-winning discovery of now 25 years ago, then the universe will continue an accelerating expansion in the future and will not recollapse. So the universe is just going to continue to get less dense and to dissipate over time.
All right. I'm going to do one more kind of combination question. We've gotten a few people asking about more amateur astronomy kind of stuff and stargazing and things like that. And I wanted to mention that this Friday, we actually are going to have myself and one of our other members of Professor Impey's group talking about specifically amateur astronomy all day on Friday. So check the schedule. We are going to put that up sometime after this stream for the specific time, and we'll talk about that at length. But Professor Impey, I was wondering if you had any specific objects for people new to amateur astronomy that you like to maybe show people, or that was your go-to, and also if you had any telescopes that you would do amateur astronomy with.
The telescope thing is, it's hard to stay on top of that, so I won't pretend to be a current expert on that. But if you look, and they have online versions or their printed magazines, if you look at either Astronomy magazine or actually better still Sky and Telescope, they have lots of ads, like a dozen or 15 or more pages of ads per issue that represent all the major amateur telescope makers. And the websites of those magazines also have reviews of those telescopes. So those are the single two best sources just for reading reviews of telescopes and for seeing what's out there on the market. If you just go to the internet, cold, then it's a little trickier because you don't really know reviews. You want to see reviews by people who are good amateur astronomers already, and that's why those magazines are better places to go. As for what to see with your small telescope or binoculars, high-powered binoculars now can do quite good service. You may want a tripod, because the big ones and the best ones are a little heavy. It's hard to hold them still when you're pointing up at the sky. So a long stem tripod is a good idea if you're really going to do binocular observations. But the standard go-to objects, of course, for small telescopes are the Messier objects, 110 of them, the first cataloged by Charles Messier in 1789, I think, French comet hunter. And these were fuzzy objects that were not moving in the sky, so they ended up not being comets, and they form most of the big, physically big or angular size big objects that you can see brightly in the night sky. And they're a combination, almost an equal combination of galaxies, a few dozen galaxies, a few dozen star clusters of various kinds, open clusters that are young or globular clusters that are old, and then various other nebulae like supernova remnants and so on. So it's a grab bag of bright sky objects, and that's why it's good to study, because there's something different in all of these. And then, of course, the other main go-to objects when you have a new telescope are the planets. The giant planets is particular because you can easily see the 4 Galilean moons of Jupiter, and sometimes you can see 7 or 8 with a 10-inch telescope, say. You can obviously see the rings of Saturn. They're not at a great inclination right now, but you can see those, and occasionally a couple of moons. And then, any other planets that are visible in the night sky. There are other star clusters. There are opportunistic comets that come and go. We just had one a few weeks ago that's now gone. There are, of course, if you want to do naked eye or binocular observing with a good wide field, you can just pick any of the meteor showers that come and go, and you'll see quite a lot. You do need a wide field view to catch those. And there's plenty to see, actually, with a small telescope. 10-inch telescope or even an 8-inch telescope will get you quite a lot.
Nice. And like I said, if people are more interested in that, we're going to be doing a stream on Friday all about amateur astronomy. All right, our next question is from Raganthan Rama. They said, "Good evening, Professor. Is it possible that with the effect of gravitational lensing, we can one day stumble upon light emitted from our own planet returning to us with a time shift? In other words, can we witness our own past?"
That's an interesting question. So gravitational lensing, in principle, I mean, if space-time were curved, but gravitational lensing is caused by the curvature of space-time by gravity. And so the lensing that we see in the universe is typically caused by galaxies on other galaxies, but it's a modest amount of curvature. The deflection angle in a typical gravitational lensing scenario out in space is a few arc seconds, maybe as many as 5 or 10 arc seconds. That's a really tiny deflection angle. If you were imagining somehow seeing light that had taken a round trip, or seeing back to your own origin, that light deflection angle would have to be 180 degrees, obviously. And the only place where a deflection angle like that happens is right around a black hole. The ergosphere is the sort of path by which a photon will just bend around a black hole without being trapped by it. So you would need a black hole as a vehicle or as a tool to see light that was coming back from the original direction. So I don't think lensing can actually help you with that. There's an interesting hypothetical experiment, which is really hypothetical. I don't think it's a real experiment, where people have speculated that if there were alien intelligent civilizations out there that have built huge mirrors, they might have a mirror pointed in our direction or some other civilization's direction, and we could see light from ourselves with a suitable time delay. And so we could look into our own past through a mirror held up by an extraterrestrial civilization. It's kind of nice speculation.
And actually, speaking of extraterrestrial civilizations, we have a couple questions about how to discover those. So some people are wondering, how would we discover intelligent life somewhere else in the universe if we aren't able to communicate with them? And what's your take on the chance of ever finding another, either just extraterrestrial life in general or another intelligent civilization specifically?
Well, the search for extraterrestrial civilizations is abbreviated with an acronym SETI, and search for extraterrestrial intelligence actually is what the acronym stands for. And those experiments have been going on since 1959, when Frank Drake, a University of California young postdoc, did what was called Project Ozma, where he used the 140-foot radio dish at Green Bank Observatory to observe 2 stars and stare at them for hundreds of hours, looking for radio signals. So the classic mechanism for looking for extraterrestrial civilizations or intelligence with technology is to look for radio emission. And not just any radio emission. There is radio emission in the universe from natural causes. In this case, you're looking for very clearly narrow bandwidth pulsed radio emission, because natural processes can't make radio emission like that. But we, of course, send pulsed messages all the time. We send information that way. And so it's a logical thing that a civilization might do. So SETI for decades has been looking for these narrowband pulsed radio signals in a particular pattern that would indicate a message or some communication of some sort. And then in the last 20 years, the other mechanism is pulsed optical signals, such as by a laser. So we have laser technology, they're very powerful terawatt lasers that could shine across the galaxy. And in principle, although the advantage of radio SETI is that stars don't emit radio emission. So if there's a radio transmitter on a planet around a star, the star is not competing with radio emission from itself. A star, of course, is optically bright, so you might think, how could we possibly see a laser? Well, we have lasers that are powerful enough to outshine our sun for a billionth of a second, a nanosecond. So basically, you look at a distant star which might have a planet and a civilization shooting lasers out, and if you can parse the light or chop it up a billion times a second, then in those short pulses, the civilization is outshining their star. So that's the second way SETI is operating. Now, as for the probability that those civilizations exist to be detected, it's essentially impossible to calculate. We just don't know enough about life in the universe of any kind, because we haven't found any, to speculate about what fraction of that life goes beyond microbes and becomes intelligent and then develops technology. So it's a shot in the dark, literally.
All right. So our next question is from one of our live viewers. They were wondering, going back to JWST, so how exactly does the JWST telescope, how will it be getting photons from the beginning of the universe, or the early universe is what they're hoping to see, when we know that the universe is under expansion at a very rapid rate, and the current width of the observable universe is over 46 billion light years?
Right. So James Webb Space Telescope is operating at somewhat longer wavelengths than the Hubble Space Telescope. The Hubble Space Telescope did have a near-infrared instrument on it, but it was primarily an optical telescope, is primarily optical, and it extends into the ultraviolet. James Webb is much more of a near-infrared telescope. It does its best work at somewhat longer than 1 micron wavelength. And that fits very well for looking at the early universe, because the expansion of the universe causes a redshift. So as photons travel through space and through the expanding universe, they are literally stretched by the expansion of space itself. And that factor of stretching becomes larger the longer they travel through space. So the further back in time you look, the more you are looking at redshift, at photons whose wavelength has been redshifted by the time you see them. And so to look back to the first stars and galaxies, you're looking at what astronomers would call a redshift of about 10. And that means that the wavelength of those photons has been stretched by a factor of 10 since they were emitted. So you have a photon being emitted by a very young star, a very young galaxy in the first billion years or first half billion years of the universe. And then in getting to us over all that space and time, its wavelength is stretched from a blue optical wavelength into a near or mid-infrared wavelength. And that's what James Webb was built to detect very sensitively. So James Webb is the perfect tool for looking back into that phase of the universe, because those waves have been stretched to infrared wavelengths. And that's really how it was designed.
Cool. And continuing with the JWST subject for just another moment, Juan Kramal was wondering, what are the main advantages of orbiting in the Lagrange point 2 for JWST that, I guess, rivals the issues if it ends up needing being repaired in some way, which is not possible at the Lagrange point?
Right. It's a trade-off. So putting James Webb at a Lagrange point 1 million miles from the Earth is a trade-off, because you've traded off an exceptional environment for doing space astronomy for the danger of what happens if it breaks and you can't fix it. So the Hubble Space Telescope has that trade-off in a different direction. The Hubble Space Telescope, of course, was serviced 5 times by astronauts. It was only, 240 miles up, a shuttle ride away. But that's not actually a great environment for space astronomy. So the Hubble Space Telescope, while it's done and still does amazing things, is quite constrained in how it observes. It can't observe, obviously, anywhere in the direction of the Earth, because there's Earthshine that's bouncing off, sunlight bounces off the Earth, diffuses through the atmosphere. So even if you're on the night side of the Earth, there's sky glow, and the Hubble Space Telescope will see that if it's pointing anywhere near it. Then, of course, you have to avoid the sun and the moon by some large set of angles. So Hubble observations are kind of limited in that way. And it's just not a super dark environment because of that Earth glow and Earth shine. And there's low amounts of debris in that orbit too. When you go to a Lagrange point, you're away from all of that stuff. So you're about in the most dark, pristine environment possible. You, of course, still have to avoid pointing directly at the sun. You have to avoid pointing at the Earth, but the Earth is 1,000,000 miles away and quite small and quite dim, so that's very easy to avoid the Earth or the Moon. And so the sky is really widely available. It's exceptionally dark, and the environment is exceptionally clean. There's no atmospheric, there's no contamination by radiation or particles or anything. It's a perfect vacuum. So that trade-off was understood. Other satellites have been there. WMAP, which was a microwave background satellite, very successful, observed for 10 years and gave us some of our best data on the microwave background. It was at L2, and there have been about half a dozen missions overall at L2. So it's a very popular place. James Webb is not the first to be there.
Great. And we may do another James Webb question at some point during this stream, but we're also going to be talking about it. We have a astronomy news stream we do every Wednesday. So we'll be talking a lot about JWST tomorrow. But our next question comes from GameStar013. Professor Impey, good morning. What does the Higgs boson particle decay to?
Well, the Higgs particle is not intrinsically unstable. Remember, the Higgs particle is not formally a particle, it's a field. So that's an ambiguity that is sometimes lost when people describe the Higgs. So we call it a particle, we call it a boson, as if it could have that type of property of being stable or unstable or decaying or not decaying. The Higgs field is a field. It's a sort of ambient mechanism by which other particles attain mass, all the particles in the standard model of particle physics. And so in and of itself, the Higgs field is not unstable. It does not decay, but it has certain properties that allow it to attribute mass to particles. Now, the mechanism of the Higgs is not fully explained in the sense of deciding why quarks have the masses they do and electrons and muons have the much smaller masses that they do. So understanding that there's a mechanism that can give particles mass is not the same as understanding why the particles all have the masses they do. So we should not pretend that the discovery of the Higgs in 2013 and 2014 completely solves all the issues of particle physics.
All right. Our next question we have is more about the study of astronomy. From Gigalodon, they say, "Hi, I'm an aspiring physics student who's just about to enter college and was wondering about pursuing astronomy further in the future. I'm really passionate about physics and find astronomy really interesting, and I'm really curious about the universe. Is there a roadmap you would suggest?" And we've talked about this once or twice, but I figured we have a lot of viewers on, so anyone who'd be interested.
Sure. So physics is an excellent path into astronomy. So if you're already interested in physics, that's a great start. Physics is the gateway drug, if you like, to astronomy. I was an undergraduate physics major. Most of my colleagues who might hold faculty jobs in astronomy, their first degree was physics, or sometimes physics and astronomy. But I actually only took 2 astronomy courses as an undergrad because my program was physics and they didn't offer much astronomy. So you will gradually get astronomy. And if you pick an astronomy physics program, say, in a physics and astronomy department, there are sort of hybrid departments in the US primarily, but also Europe and elsewhere, then you'll get more astronomy in your undergraduate work. But it's okay to do a pure physics degree with just a few astronomy courses and then get most of the astrophysics you really need to be a professional at graduate school, because grad school, will have a complete set of courses to bring you up to speed on astrophysics, and that's how most students get their training. You also, along the way, are going to have a lot of math because, astrophysics is the application of physics to the universe, and the techniques are often highly mathematical. And of course, now in astronomy and astrophysics, simulations are a big part of what astronomers do. And so there are skills involved in computation and programming and in application of numerical methods to understanding the universe. So these are the kind of skills that are a little newer in terms of the curriculum, but there's things you should look for in a program.
Sorry, missed the button for the unmute. All right, we have our next question is from our email, which I am going to drop the email in chat if you guys are interested. From Faisal, they ask, is it possible to use radioactive radiation or any kind of electromagnetic waves to study the history of the universe, similar to the infrared technology in the JWST? And then someone in our live chat also asked about like what are some of the oldest objects that we know about or that we've been able to see.
I'll take the question as referring to radioactivity and the radioactive process in terms of being able to do cosmology or look at the history of the universe. So it's an interesting question. Radioactivity is a fundamental physics process that takes place, of course, on the Earth, and we can study radioactive isotopes and their decay rates, and that's how we age date things. That's how we know the age of the Earth and the Moon to about 1% precision. These methods are useful in a slightly less precise way to talk about the age of the universe. So a cross-check, a very important cross-check on the age of the universe as inferred from the expansion history, which is a little indirect because it depends on that model, is to try and use nucleocosmochronology, as it's a mouthful, that term, but it refers to age dating through nuclear decay. You can find the suitable isotopes out there in the universe and infer the oldest rocks or oldest materials, and therefore how long the universe has been around. It's an important cross-check because if you used that age inference and came up with an age of 20 or 25 billion years, it would be violating the Big Bang model. It would be a crisis for cosmology. And so even though it's not as precise as the other measurements of the age of the universe that use the model itself, it's a very important cross-check. And so use of those radioactive isotopes has produced ages for the universe that have an error bar maybe of 3 billion years, and they're around 15 to 16 billion, which of course encompasses the age measured through the Big Bang model. So it's a very important independent test of the age of the universe using fundamental physics essentially, and no model at all.
All right. We've had a few people ask, we had a question before about the expansion of the universe, and a few people are asking what exactly is the universe expanding into? So could you answer that?
Well, so it's a fair question. If you hear the universe is expanding, you wonder what's it expanding into, because in a terrestrial situation, you can imagine, inflating a balloon and it's expanding into the room, into the place you're standing. But this is not the same situation. The expansion of the universe is the unfolding, if you like, of space-time since the Big Bang. And the construct, the model, or the concept does not have anything external to it. So you can explain an expanding universe using general relativity without reference to an external medium. In other words, it's not required. So part of the answer, maybe a slightly frustrating part of the answer, is it's not a relevant concept. It's an unnecessary addition to the idea to add that it's expanding into anything. It's not necessary, so you don't introduce it. There's no way to measure it either. And so we have that's the theoretical limitation, that it's not required to have an external medium. And then the practical limitation is that we exist in this expanding space-time ourselves, and we're limited in our view of it to things that are where light can have reached us in the age of the universe. So we can't look beyond the observable universe because our view is literally limited by light travel time. And so that's not a fundamental limitation. That's not the edge of space-time. That's just a limitation due to the way light travels over 13.8 billion years.
All right. We have a question from Adawaith, one of our live viewers. They said, "Hi, sir. Can we humans make a life suitable for living on Mars by genetic engineering or other means?"
So the ability to live on Mars is an interesting question, and it's becoming a real question because we do think there will be a Mars colony or settlement, a very simple one with only a small number of people there, probably being resupplied from the Earth and probably not spending their lives there. but we can imagine this will happen within maybe 15 to 20 years. It may happen through the private sector and Elon Musk and SpaceX, or it may happen through NASA and its partners. So it's a fair question to ask, what would it take to live on Mars? So in the near term, and the way it's being planned, the only way we'll live on Mars is by protecting ourselves from an exceptionally harsh environment. There's obviously no air, essentially no atmosphere. There's enormous amount of radiation because the magnetic field is weak or almost absent, so it just plows in, and that's very damaging to genetic material. So people living on Mars will be in, battle-hardened domes, not translucent domes that let you look out at the night sky and the Martian landscape, but domes that are clad in probably Martian soil that's been turned into building materials, and have a few feet thick of that material covering you in tiny little portholes out. So that's what it'll take to live on Mars in our current state. So the more visionary, futuristic way of imagining it is to say, well, okay, that's in our current state. What would we do to ourselves to make ourselves more adaptable or more easily able to tolerate the Martian environment? We're always going to need air to breathe. So that's not possible by genetic engineering to imagine us being able to do without air. So we'll need an atmosphere to be generated. But it is actually possible with genetic engineering to make us more resistant to radiation damage. That is certainly within the sight of modern genetics. And so I suspect that's the kind of adaptation that will be pursued for people who choose to live on Mars, to make them more resilient, essentially, to a very tough radiation environment. And then the other part that may happen is you're dealing with much weaker gravity, and that has an effect on the organism, on the organs, on the bone structure, and so on. And I think adaptation to that over a human lifetime will be very limited, of course, but genetic engineering could once again make humans better able to function normally by changing. You could genetically engineer vascular function and so on to make us behave better in weak gravity than we would otherwise. So those things will probably happen in the future, and we're talking decades and decades now, maybe a century.
Very interesting. All right, we have another question from one of our email viewers. So Wendy Traver asked, is the prevailing theory that comets deliver the water to Europa, or is there a different prevailing theory?
The theory of where Europa and other solar system objects got their water is still in discussion, I would say. There are competing ideas. It's still an unresolved issue where the Earth got its water. So the delivery of water around the solar system, the inner solar system and the outer solar system by comets, it's a well understood mechanism, because comets do have a lot of frozen water and other volatiles embedded in them. And when they come into the inner solar system, or when they plow into objects, they deliver those frozen elements, and including frozen water. That story doesn't work really well for the Earth, because there's an isotopic mismatch in the isotope rate we've measured for water in the places we've seen it, in a couple of asteroids, for example, and in one comet, compared to the Earth's oceans. So there's a mismatch there. Now, we don't know what the isotopic balance of the European water is, because we've never sampled it or measured it. So we're speculating a bit. But the best guess, again, is that either the water was delivered by comets and water-rich material, or that it was present in the formation of the moon itself, deep into the material of the core and the mantle. And then it was gradually, in the formation phase, when the moon was cooling, it was extruded out towards the surface where it became an ocean. That's still a viable idea for the Earth, too.
All right. Just wanted to say thank you again to everyone for these lovely questions. We have so many today, so just wanted to say, if you don't get your question answered today, we do these Q&A sessions every 2 weeks. We switch between the channel here and our channel on YouTube, which I will link in the chat in just a moment, so you guys can definitely come back and ask those questions again. But our next one right now is from Roros. They said, what data is considered, so I'm assuming what goes into the or well, they say what data is considered when determining the tidal locking of an exoplanet. So I think they mean, what allows for the tidal locking of an exoplanet or a planet in our own
Right.
smaller planets in our solar system.
So to calculate the tidal force, which exists between any two objects in a gravitational situation, and understand at which point it becomes tidal locking, you really only have to know basically three things. You have to know the mass of the star that it's orbiting, which could be a normal star like the sun, or now some cases it's a red dwarf, a rather small star. You've got to know the mass of the planet itself, and you've got to know its size as well. Those are different, of course, because planets can have higher or lower density, and so a planet of a certain mass may be larger or smaller. The size matters because the tidal force is the difference in the gravity caused by the star on one side of the planet versus the other side of the planet. That obviously acts as a stretching force because it's a differential gravity. And it's when that differential gravity reaches a certain threshold that it can overcome the natural spin rate of the planet and lead the planet to be tidally locked, which essentially means that one side of the planet faces the star always. And the moon is an example in our solar system of the one side of the moon facing the Earth always, because the moon is tidally locked to the Earth. Mercury is tidally locked to the sun. So these tidal locking situations exist in the solar system, and we know they should exist with exoplanets. But to know the mass and the size of an exoplanet is a slightly higher bar than just what we usually have. Most exoplanets are either discovered by the Doppler method, which gives you a mass, or by the transit or eclipse method, which gives you a size. So it's only the subset for which we have both measurements, which is a few hundred exoplanets out of 4,000 roughly, where we can judge whether it might be tidally locked. And obviously the tidal locking is preferentially going to occur in the planets that have the tightest, closest orbits to their parent stars.
All right. Our next question is from Abhinav 2010 Spock. They ask, how can we prove the universe is 13.8 billion years old?
Well, the age of the universe is not a hard number that I think you can absolutely take to the bank like the age of the Earth. So just to make the comparison, the age of the Earth and the Moon, the Earth-Moon system, is measured by radioactive decay, by finding primordial rocks and measuring the decay rate and then seeing what the ratio of parent and daughter isotopes is. And that is a precise method that you can cross-check with different isotopes, and it leads to an age of 4.54 billion years, and the error is really in that second decimal place. That's very accurate. Our measurement of the age of the universe is not as precise. I'd say it's perhaps at the level of 100 million years, so it's 13.8 plus or minus 0.1. It's still pretty accurate, but not as accurate as the age of the Earth. And it essentially is coming from the expansion model. We are talking about an expanding universe, which the motion of the expansion is dominated by dark energy and dark matter. So it depends on our measurement in the local universe and beyond of what the contributions of dark energy and dark matter are. And then you make an expansion model, and that expansion model gives you an age. So that's fundamentally where the age comes from. It's not nearly as direct as measuring an age, say, through radioactive decay.
All right. Our next question is from Prab 1307. Can future technology based on gravity waves break the limit of the speed of light for observing the universe in a better way?
So the gravitational waves or gravitational radiation that we've now detected, starting about 5 years ago in 2016, it is, in the theory of general relativity, this radiation is a disturbance in space-time that propagates with the speed of light. So according to general relativity, which has been affirmed in the detection of all these gravitational waves because they have the properties we would expect from the theory, that they do not obviate or get you around the limitation of the speed of light as a fundamental limit to communication. They are propagating at the same speed as electromagnetic radiation. That's according to the theory, and that's been pretty much confirmed by observation too.
All right. I'm going to grab another question from our emails real quick. So let's see. We have one going back to the James Webb Space Telescope, because that is the big topic today. Jen Campos asked, when the James Webb views the early universe, do you expect the structure of galaxies to be very different? Will they be packed closer together? Will they look different?
Well, that's part of what we want to find out. I mean, it's not a dramatically new regime for the James Webb. We shouldn't exaggerate it too much. Hubble Space Telescope has been very successful in measuring distant galaxies out to redshift of about 6 or 8, which is distances that correspond to about 1 billion years after the Big Bang. So it's not a dramatic improvement, but it's a substantial improvement because Hubble was not able to get back to the very first epoch of star and galaxy formation. James Webb should. The difference is that when James Webb is looking at a redshift of 10, say, a factor of an order of magnitude expansion of the universe or stretching of the radiation, that is obviously a universe that was 10 times smaller and a 1,000 times denser than the universe now. And it was 10 times hotter as well. The radiation was hotter. So it is a different place. It was a different place back then when the first galaxies were forming. So necessarily, of course, the young galaxies were much closer together in space because the density was 1,000 times greater. And the galaxies we also think were much smaller because the view of galaxy formation is called a hierarchical model, where dark matter, even if we don't know exactly what it is, it has the properties that mediate the formation of big things from the collisions and mergers of smaller things. So we think that galaxies grew bottom up from smaller pieces, but dwarf galaxies or even massive star clusters, gradually combining to form the biggest galaxies that we eventually see in the universe around us. That's the theory, but we are going to be able to check it in quite a lot of detail with James Webb.
And still on the a little bit on the subject of JWST, because it will be observing some exoplanets and things. We have a question from Adawaith that is basically about how if we look at distant planets, we are seeing them in the past compared to where we are in time because of the delay of light. So if we see a distant planet that may not seem suitable for life, but is in the future, like how would we determine if some planets might become suitable for life in the future?
I mean, it's an important issue that astrobiologists are well aware of, which is that the general issue is that the habitability of a planet changes over time. For example, the Earth, has had life on it for 4 billion years, but those first few billion years were only inhabited by microbes, and we could not, plants and animals could not have tolerated those environments. So habitability of a planet changes, including our planet, and that's going to be through cosmic time true even into the future. In practice, though, this is not really an issue because most of the exoplanets, the 4,000 that we've found, mostly through the Kepler satellite, are relatively nearby. They're in the backyard of the galaxy. So the typical distance to most of the exoplanets that have been cataloged is a few hundred up to a few thousand light years. And that, in a galaxy 100,000 light years across, is a small fraction of the Milky Way. It also means that the light travel time to those planets is only at the most a few millennia. So we're not really seeing them very far back in time. And we don't expect the habitability of any planet to change substantially over millennia. Obviously, you can have ice ages and things like that, but the gross habitability of a planet takes longer to change. So really, the distance and the light travel time is not an issue as far as habitability and what we're measuring now, as opposed to the time the radiation was emitted.
All right, and apologies if you guys can hear some noise on my side. There's some construction going on in my building. But another question related to JWST, Sarcastrophe143 asked, can you emphasize about trim flaps on the JWST and its role in observation?
Well, I'm not sure exactly what the question is referring to, but so I think I'll pass on this one. This is a technical issue that I'm not familiar with. I've heard the term, but I'm not savvy enough about it to give a good response.
For sure. Actually, in exchange, we had a question earlier that I don't believe I asked you, but I was curious about as well. What is the JWST, once it gets to its Lagrange point, what is its main source of power going to be?
It has solar power, of course. It has large solar panels, and that's the standard mode of powering pretty much any spacecraft. The only exceptions to that in space exploration, telescopes, and everything is the outer solar system. When you send an object far from the sun, solar panels no longer do the job. And so for outer solar system missions, we typically use RPGs, as they're called. That's an acronym from NASA. And these are just really little radioactive power units based on plutonium. So for most spacecraft, including the Hubble, including James Webb, you're using solar panels and solar power. And you're hoping that those panels don't degrade too much over time.
All right. And I think we have time for about 2 more questions, I would say, if that works for you.
Mm-hmm.
So we have one from Rashmi RD, and they say, hello, this is a question from my 8-year-old son who's watching with me. Hello. He would like to know, how big can a black hole be, and what is on the other side of it?
Well, that's a good question. A pretty good question from an 8-year-old or anyone. The biggest black hole, we don't know what the biggest black hole can be, but the biggest black hole that's been measured in the universe is a massive black hole in the center of a galaxy that has a mass of about 20 billion times the mass of the sun. So phenomenal massed black hole in a very big galaxy. So the galaxy itself has about 1 trillion times the mass of the sun of stars. And that's about as big as a black hole can be, just growing as fast as it can at the center of a galaxy over 13 billion years. So even though we haven't found anything bigger, we sort of think that that's a practical limitation on the black hole mass. And as for what's on the other side of the black hole, well, a black hole is just an object, and so on the other side of the black hole, in the center of that galaxy, for example, are just more stars and part of the galaxy. In fact, you can get to see around the other side of a black hole because the black hole focuses and lenses light. So a black hole, by bending space and time and bending light, actually lets you see behind it, whereas a normal object would just block your view. So that's a nice feature of a black hole, you might say. So thanks for all those questions. Great variety as usual. And thanks to Vicki for facilitating. And I don't think we've announced our next couple of sessions, but we will soon. And we'll keep to our cadence of every other week. So thanks to you all, and we'll be back with you in a couple of weeks.
And in the meantime, like I mentioned, we have many other streams that we do on this channel. Every Wednesday, we do an astronomy news stream. Every Friday, we do something a little different related to astronomy. And every Monday, we play a fun space-related video game. So please, if you're new here, give us a follow. If you're interested in supporting us even more, you can subscribe. And yeah, we'll see you next time. Thank you so much, Chris, and I guess that's it. Bye, everyone.